chapter 9. And I think I remember one of the last things we discussed in class last week. In fact, I think it was the very last thing we discussed, and that was the Born-Haber cycle. And I noticed that one of the questions in chapter 9 is actually dealing with that very same topic. All right. So let's see here. I want to know, unfortunately, the questions in chapter 9 are not ordered in the same order as outlined in the video. So what I'm going to do is scroll down to this question, which is dealing with the Born-Haber cycle that we just talked about last time. It's a bit smaller, so. Oh yes, unfortunately the printer upstairs is kaput. Yes, it's kind of annoying. We instructors were commiserating about it earlier. So I apologize for that. So let me see, for you guys out there in Zoom, let me see if I've published it. Yes, I have. So you guys should be able to download it. And you guys here, if you have your devices, you can probably get it from there as well. Okay, where did oh, here it is. Okay, so this is dealing with the Born-Haber cycle. All right. So if you remember, the Born-Haber cycle basically maps out the changes that a metal and a non-metal undergo in order to form the ionic compound. All right. So we discussed that last time, and this is an application of this problem. Now, this question gives you the Born-Haber cycle for cesium chloride, right? So this is cesium here in the solid state and chlorine. If you go from cesium to chlorine, if you go from cesium and chlorine to cesium chloride directly, this is the amount of enthalpy change taking place, right? And then you see here that the first step represented by H2 going from cesium solid to cesium gas, that would be sublimation, and then the chlorine forming, the cesium gas forming the cesium ion, that would be the first ionization energy, and then going from chlorine molecule to chlorine gas, that would be the bond dissociation energy, and then the chlorine getting the electron here to form the chloride ion, that would be electron affinity. And then if you remember, I said that in your textbook, the lattice energy definition is the enthalpy change when you go from the solid compound to the gaseous ions, right? So I'm going to remove this arrow here and put the tip of the arrow here, right? So that would be the lattice energy. So they gave us this, and the question is asking for you to give the names of the enthalpy changes represented by delta H1, delta H2, and delta H5, all right? So let's see here, delta H1 is where we're going from the elements themselves to the compound, the ionic compound being formed. So that would be enthalpy of formation. Enthalpy of formation, all right? And then delta H2 is where we go from cesium solid to cesium gas. So that would be enthalpy of sublimation. Remember, sublimation is what happens when a solid is converted to a gas without going through the liquid state, all right? And then delta H5, which is going from here to here, where the chlorine gains an electron, the chlorine gas gain an electron to form the chloride ion, that would be electron affinity. All right, so that's basically how we get those terms, all right? So that answers the A part of this question. So let me scroll down to see what the B part says. Okay, so B part is asking for you to calculate the value of their lattice energy, which is delta H6. So as I said before, let me clear this up here. As I said before, the lattice energy is the energy required to break up the ionic compound into its gaseous ions, right? So the question is asking for us to find this energy here, which is defined in your textbook as the lattice energy, all right? So basically, we can conclude that delta H2, which is this here, plus delta H3, plus delta H4, plus delta H5 will be equal to delta H1 plus delta H6. All right, because going from here all the way around to here will be using the same energy change as going from here to here. All right, what the question is asking for is asking for delta H6. So let me just write here delta H6 will be equal to delta H2 plus delta H3 plus delta H4 plus delta H5 minus delta H1. All right. So all we have to do now is plug the numbers in. Delta H6 is equal to delta H2. What's delta H2? Plus 79 kilojoules per mole plus delta H3, which is plus 376 kilojoules per mole. And then delta H4, which is plus 121 kilojoules per mole. And then over here now, delta H5, we're adding that will be minus 364 kilojoules per mole. And then now subtract delta H1, which is minus 433 kilojoules per mole. So that's basically the setup. Get my calculator. Oh, don't got it. Okay, let me get the point instead. Okay, so 79 plus 376 plus 121 minus 364, and then minus, so that's plus 433. And according to my calculation, this works out to be equal to, please correct me if I'm wrong, but I got 645 kilojoules per mole as the answer. All right. Any questions about this one? Any questions? Any questions? Okay, so that's the answer to the B part. Here, okay, so there's a C part, which is asking, explain why the interact represented by delta H3 has a lower magnitude for cesium than sodium. All right, so we have to go back to the diagram. Let me clear this here again. Okay, so it says delta H3, right? It has a lower magnitude for cesium than sodium, right? So delta H3 is this right here. So delta H3 involves the conversion of the cesium gaseous atom, which is this, to the cesium gaseous ion by the loss of an electron, right? So basically what the question is asking is, why is it that cesium has a lower value of this energy compared to sodium? All right. Now you have to look at their relative positions in the periodic table, right? Cesium is basically the second to last element from below in group 1A, and sodium is like the third element, right? So sodium is above cesium in that group, right? And the energy that is represented by delta H3 is the first ionization energy, the energy required to remove the valence electrons. So why do you think that cesium has a lower first ionization energy compared to sodium?
Because sodium smaller
Okay, smaller atom, and therefore,
has a tighter valence shell requirement for energy to remove.
well, it has to do with, you started off right. The sodium atom is smaller compared to the cesium atom, right? And therefore, what would you expect the effect that would have on the valence electron? Because remember, the valence electron is the electron that is being removed.
Right.
So therefore what?
Tighter affinity.
What's that?
Tighter affinity.
Okay, so okay, or the attractive force is stronger between the nucleus and the valence electron in the case of sodium compared to cesium. So therefore, it is harder to remove the sodium, the valence electron in sodium compared to that in cesium, right? So let me just put that in words in answer to that question. Here, let me clear this. Let's go down. So because cesium is larger than sodium, the force of attraction between the nucleus and the valence electron is lower, and therefore that electron is more easily removed compared to sodium, compared to that of sodium. Please forgive my poor handwriting. All right, so that's basically it, right? The cesium atom is larger than the sodium atom, so therefore the valence electron is more easier to remove in the case of cesium because it's further away from the nucleus, weak attraction between the nucleus and that electron. So therefore you can more easily remove that electron in the case of cesium compared to sodium, and that's the reason why cesium has a lower first ionization energy compared to sodium. Okay. Any questions about that? Any questions? Any questions? All right, let me clear this. So I'm going to go back to the top question, the first question in the assignment, which deals with a term, electronegativity, which I covered in the videos. Briefly put, or simply put, the electronegativity of an atom is the tendency of an atom to attract electrons that are being shared between itself and another atom, right? So basically, the greater the attraction for shared electrons by an atom, the greater would be the electronegativity, right? And a guy by the name of Linus Pauling, a very famous scientist who won a couple of Nobel Prizes, one for chemistry and one for peace, I think. He came up with a table based on some thermodynamic measurements, which basically what he did was create a 4-point scale, right? And basically 4 would represent the highest electronegativity. And based on certain measurements, he came up with a table which I have included in that packet. I'm looking for it to show you what table I'm referring to. And that's the table that you're going to use, of course. No, not that. This. Okay. I think it's the very last page, if I'm not mistaken. Yes, it's the last page. So this is the table that he came up with. If you look in different textbooks, you'll see some different variation in numbers. So for the sake of consistency, we're going to stick to using this particular table, right? So this table basically lists all the elements, or most of the elements, and their corresponding electronegativity values, right? So as you can see from this table, of all the elements that exist, fluorine has the highest electronegativity values. And there are some trends that we discussed in the videos concerning electronegativity. For example, going down any group, the electronegativity would decrease. And going from left to right of any period, the electronegativity would increase. All right. So this is the table that you're going to use to answer this question, because this question is asking for determine the type of bond that will form between each pair of atoms in the table below. And you're going to use the electronegativity chart that I showed you. So basically, there's a criteria. Again, different textbooks will have different criteria for determining what type of bonding that will exist between any two elements. So let me just give you the criteria that I gave in the video. So if the difference in electronegativity, I'm just going to create a small table here. Right, in one column, we'll have the difference in electronegativity values, and this here will give you the bond type. So if the difference in electronegativity goes from 0.0 to 0.4, then the bond type associated with that would be nonpolar covalent. So what do we mean by nonpolar covalent? Basically, what we mean is that the electrons are evenly shared between the two atoms that are connected by that bond. All right. So if you have two identical atoms like oxygen, one oxygen bonded to another oxygen atom, or chlorine, one chlorine bonded to another chlorine atom, then obviously there's no difference in their electronegativity values. So therefore, the electrons that are shared between them will be shared evenly. All right. Now, if the difference in electronegativity ranges from 0.5 to 1.7, then that bond is considered to be polar covalent. Right, and what that means is that the electrons are shared unevenly or unequally between the two atoms, right? So for example, if you have oxygen bonded to fluorine, right? Based on the table, let me go back to the table. Based on the table, right? This is oxygen and this is fluorine, right? So the difference between them is 4.0 minus 3.5, so that's 0.5, right? So that would belong to the polar covalent type of bond. What that means is that electrons will be unevenly shared because fluorine is more electronegative than oxygen. That means the electrons will spend, the shared electrons will spend most of the time closer to the fluorine than the oxygen. All right. So that's an example of a polar covalent bond. And then finally, if you have a electronegativity difference being 1.8 or greater, then the bond is essentially ionic, right? So what that means is that you have a complete transfer of electrons from the metal to the non-metal, or from one atom to the other, right? So therefore, these are the three categories of bond types that the question is asking about. You have the nonpolar covalent, where the difference in their electronegativities would be between 0.0 and 0.4. Then you have the polar covalent, where the difference in their electronegativities will be between 0.5 and 1.7. And then finally, which is the most extreme, ionic, where the difference in the electronegativity of the atoms involved would be 1.8 or greater. All right. So with that said, we can now look at question number 1 in this assignment, where they gave you two different atoms, atoms 1 and 2, and you're to calculate the electronegativity difference between them using that chart. And then you're going to tell whether or not the type of bond involved is either nonpolar covalent, polar covalent, or ionic. All right. Now, I'm going to need your help because to avoid me switching between this document and the tables, I need you to tell me what the electronegativity values for each of these elements are, starting with sulfur. So can somebody, I'm sorry, not sulfur, arsenic. So can somebody tell me what arsenic, what's the value for arsenic? Nobody has the electronegativity values in front of them?
I just.
Oh, okay. 2.0. Okay, I'll take your word for it. And what about sulfur? What's the value for sulfur?
0.5.
2.5, right? So 2.5 minus 2.0 gives you 0.5. So what category of bonding would you put that at?
MP or covalent.
Polar covalent, exactly. All right. And basically you do the same for the others. So what I want you to do right now is to complete this table. All right. Just find the difference. Well, find the values first for each of them, and then find the difference. And then just work out the difference, and based on the difference, you determine what type of bond we're dealing with. All right, so we are to remind you bond type. So 0.0 to 0.5, that would be non-polar covalent. 0.5 to 1.7, that would be polar covalent, and 1.8 to greater would be ion. And let me know when you're finished with that part of it.
Do you have this handout or? is this-
No, unfortunately. The print upstairs have been active up, so none of us have been able to.
Yeah.
Print anything.
Honestly, count the ones at home. Honestly, count the ones at home. Right now.
I'm sorry? Oh, well, yeah. Yeah, we instructors are upstairs complaining about it. You can just, for now, you can just write it on a sheet of paper and then you can print it from Canvas, transfer your information on.
Yeah. I guess I just don't have my table, so
Oh,
I would, but. Actually, get this, book, that table, that file is. Yeah. Oh, all right.
Yeah, that's what I'm doing.
okay. Oh, okay.
Sorry.
Yeah, no problem. I was just looking down on the other stuff.
Thank you. Thank you.
Hydrogen and oxygen.
Calcium, sulfur, iron, carbon. All right, I'll take your word for it. So let's go down to the next question, which deals with drawing the Lewis structure. Now, I went through several examples in the videos concerning how to draw the Lewis structure of a molecule or ion. And just to, let's see if I can break this up here. I can quickly go through the steps involved. All right, so let me scroll down. Okay, so basically, when it comes to Lewis structures, it's basically a combination of the Lewis symbols that represents the type of bonds, covalent bonds mainly, that exist between atoms, right? A couple of things you need to be aware of when it comes to drawing Lewis structures. In most cases, the Lewis structure shows the bonded atoms with the electron configuration of a noble gas. That is, atoms obey the octet rule, and hydrogen will obey the Dirac rule. But there are exceptions to this, which you're going to see, I think, later on. The shared electrons can be counted for each atom that shares them, so each atom may have a noble gas configuration. And let me see here. Oh, very important for you to make a distinction between what are known as the bonding pairs and the lone pairs of electrons, all right? Bonding pairs are those pairs of electrons that are shared between the two atoms, and the non-bonding pairs or the lone pairs are those that are not shared between atoms, all right? So to give you a simple example, This is a chlorine molecule. As you can see, before each chlorine atom has 7 electrons. But what happens when they come together is that these two chlorine atoms will share the same electrons that each of them had before. So now each chlorine will have 8 electrons on their outer shell. And in terms of the distinction between bonding and non-bonding electrons, the bonding electrons are those that are shared between the two chlorine atoms, and the non-bonding electrons are those that are not shared, as you can see here. Chlorine on this side has 6 non-bonding pairs, this has 6 non-bonding pairs, but they both share a bonding pair of electrons, all right? Another way of representing the Lewis structure of a molecule like chlorine is that we can use a line instead of 2 dots to represent the shared electrons, as you can see here. So this and this both represent the same thing. And in fact, we can take this further because I've seen in some chemistry literature where you can represent the Lewis structure of chlorine, for example, like this. Cl, Cl, and then you have these lines here. So each line represents a pair of electrons, right? So you can use this, you can use this, you can use this. Personally speaking, I prefer to use this, but I will not penalize you if you use the other types of representation. All right. Okay. Some other things I need to say about. So these are some examples of Lewis structures for certain molecules. So this is methane, carbon bonded to 4 hydrogens, right? So basically, you have 4 bonding pairs between the carbon and each hydrogen atom. Then we have ammonia, which has, in the case of nitrogen, 3 bonding pairs and 1 lone pair on the nitrogen atom. In the case of water, there are 2 bonding pairs, 2 lone pairs, and in the case of hydrogen fluoride, you have 1 bonding pair and 3 lone pairs. All right, so that's basically some examples. And let me just say at this juncture that when it comes to drawing the Lewis structures of molecules, we are not concerned about the 3-dimensional shapes. That is for later on, all right? For now, we're just concerned with, when it comes to Lewis structures, how the atoms are connected to each other, right? The bonding pairs and so on, we're also concerned with. But we are not concerned with, at this juncture, the shape of the molecule. So therefore, you can draw the Lewis structure of water looking like this. Something's missing here. You're going to have 2 lone pairs, one here, right? So basically, you can draw like hydrogen, oxygen, hydrogen in one straight line, or you can have it written like this. It doesn't matter. They're both legitimate and correct Lewis structures, all right? So we're not concerned with the shapes. That's for later on, all right? So you can have situations where you have multiple bonding taking place, like in the case of carbon dioxide, where you have more than a pair of electrons being shared between the 2 atoms, all right? And in the case of nitrogen, you can have 3 pairs of electrons. So this is called a double bond. This is called a triple bond. The bond where you have only 1 pair of electrons being shared, we call that a single bond. And believe it or not, you can have up to a quadruple bond, but that's beyond our scope in this course. Let me just keep this here for the time being. Okay, so these are the steps involved in drawing a Lewis structure, right? Which we're going to apply to the question being asked. So basically, you need to put together a skeletal structure that shows the arrangement of the atoms. If hydrogen is present, then hydrogens will always be the terminal atom. And what that means is that after hydrogen is bonded to one other atom, it cannot be bonded to another atom, right? So that is true for any molecule that contains hydrogen. Hydrogen can only have 1 bond, and therefore it cannot be bonded to 2 atoms at the same time, or it cannot be doubly bonded to 1 atom either. The central atom of the structure is usually the one that is lowest in electronegativity, all right? And then we have the situation of oxyacids, where if you have hydrogen atoms in oxyacids, they must be bonded to oxygen atoms, all right? And then finally here it says molecules and polyatomic ions usually have compact symmetrical structures. So those are just some guidelines for determining the Lewis structure. Now there's a step-to-step description right here. First, you determine the total number of valence electrons. Then you write a possible skeletal structure and connect the atoms by single bonds. And then you place pairs of electrons on the surrounding atoms so that each atom, excepting hydrogen, of course, will have an octet. And then assign any remaining electrons as lone pairs around the central atom. And then if necessary, move one or more lone pairs of electrons from the terminal atom to form a bonded bond to the central atom. So the best way to learn this is, of course, is to do some examples, and we have some examples right here. So I think it's important that we do these examples first before we move on to the actual questions in the assignment. So let me open. Okay, so the first example is nitrogen trifluoride, all right? And I think I went through this in the videos, but I'm just gonna go through it again. Here. So the first step in this process is that we figure out the number of valence electrons total in the molecule. So what we do is go to the periodic table and we look up the group numbers of each of these elements. Starting with nitrogen, it's in group 5, so that will contribute 5 valence electrons. In the case of fluorine, it's in group 7, but because there are 3 of them, we have to multiply that by 3, so that gives you 21 electrons. And then we add them up. 21 plus 5 gives you 26 electrons. And what I like to do at this juncture is that I express this as pairs of electrons, right? So this will equal to 30 pairs of electrons, right? So the next step is that we find out what the central atom is, and usually the central atom is the least electronegative element, which in this case would be nitrogen, and then we surround it with the other atoms. And as I said before, we are not concerned about the shape, so it's not really important how you surround the nitrogen with the fluorine, right? Now, please note, we have worked out that we have 13 pairs of electrons to assign, right? So the next step is that we put the bonding pairs first. 1, 2, 3. So we have used 3 of the 13 pairs. Then we start putting electrons around the terminal atoms. 4, 5, 6, so that has an octet. 7, 8, 9, so that has an octet. 10, 11, 12. So we have used up 12 of the 13 pairs. So the question is, where does the 13th pair goes? And the answer is, it goes right there. And that would be the Lewis structure of nitrogen trifluoride. That's how you do that. All right? Any question about this one? Any question? Questions? Okay, so let's look at the next example. Next example is sulfur dichloride. So SCl2. So based on what we said before, we go to the periodic table and we look up the group numbers for each element. In the case of sulfur, if you look that up, that's going to be 6. In the case of chlorine, if you look that up, that would be 7. But because we have 2 of them, we have to multiply that by 2, right? So that's 40. So 14 plus 6 gives you 20 electrons, which would be equal to 10 pairs, right? So we put the sulfur in the middle, surrounded with the chlorine, because sulfur is is less electronegative than chlorine. And then we start the bonding pairs first. 1, 2, then the non-bonding pairs around the terminal atoms. 3, 4, 5, 6, 7, 8. So we have used up 8 of the 10 pairs. So the last 2 pairs will go here, and that would be it as far as the Lewis structure of sulfur dichloride is concerned. All right. So that's basically how that is done. Any questions about this one? Any questions? All right. Let me clear this. And what's the next one? Next one is, okay, silicon tetrachloride. So SiCl4. Okay, so based on what we did on the previous 2 examples, what's the first step? Can somebody tell me?
Like total valence electron.
Okay, so what's the number of valence electrons for silicon? 4. What's the number of valence electrons for chlorine? 7. But because we have 4 here, we have to multiply that by 4. So 4 7s, 28, right? So that gives you a total of 32 electrons, which will equal to 16 pairs. All right? So we put the silicon in the middle, surrounded with the chlorines. So what's the next step?
The bonding pairs.
Bonding pairs, right? So remember now, we have 16 to play with, right? So 1, 2, 3, 4, right? So I've used 4 to 16. What next?
For the surrounding pairs.
Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're using all 16 pairs. So therefore, that would be the Lewis structure of silicon tetrachloride. All right, very good. Now, things can be a bit more complicated. Let's see here. Before we get to the more complicated situations, we need to understand this concept of formal charge. So formal charge is basically the difference between the number of valence electrons in a free atom and the number of electrons assigned to that atom when it is bonded to other atoms in a Lewis structure. Now, there's a formula that I use to calculate the formal charge. You might see it expressed differently in different textbooks, but this is my preference, right? So let me give you the formula that I use to calculate the formal charge. And that formula is here. Okay, so the formula that I use for the formal charge is formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons. Right? So that's a formula that I use. I think in your textbook, it's expressed a bit differently, but it calculates the same thing, right? Now, this is important when it comes to writing down or drawing the Lewis structures where you have multiple bonding taking place, all right? Now, in actual fact, if you're given a question to determine the Lewis structure of anything, this should be a part of your showing your work, right? Now, I did not do this for the previous problems because I already knew that the formal charge for those atoms would be 0. So for example, let's look at this molecule that we just worked with, silicon tetrachloride, right? This was the answer that we got. Right? So if you were to calculate the formal charge of the silicon, right? That will be equal to the group number. The group number of silicon is 4 minus half the number of bonding electrons. So for silicon, the number of bonding electrons will be 2, 4, 6, 8. So half of 8 minus the number of non-bonding electrons. There are no non-bonding electrons, so that will be 0. So when you work that out, that will be 0, right? So therefore, silicon has no charge on it. And then we do a similar calculation for the chlorine. Now, the calculation that you do for one chlorine atom will be the same for the others because they all have the same electronic arrangement, right? So I'm just going to do the calculation for one chlorine atom. That will be the group number of chlorine, which is 7, minus half the number of bonding electrons, which is 2, minus the number of non-bonding electrons, which is 2, 4, 6. And what does that give? 0, right? So therefore, there are no charges on the chlorine, there's no charges on the silicon, so therefore the entire atom is neutral, right? So that's how you calculate the formal charge in these cases. Now, there are other cases where that will not be the case, right? And I think in the PowerPoint, there are some questions to that effect. Okay, 3 good questions here. The first one is COCl2. So let me go back here. And let me get rid of all this. Okay, so COCl2. So we're going to go through the same steps as we did in the previous 3 examples, right? Start off with finding the group numbers. So carbon will give you how many valence electrons? 4. Oxygen will give you how many?
6.
6. And chlorine will give you how many?
14.
14. 2 times 7 equals 14, right? So when we add this up, you're going to get 4 and 6, 10, 10 and 14, 24 electrons, which will be equal to 12 pairs, right? So we put the carbon in the middle, surrounded with the oxygen and the chlorine. Again, it doesn't matter how you put them around. All right. So we start off with the bonding pairs. 1, 2, 3, right? Then 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. The next step in this process is that we calculate the formal charges of each of the atoms, right? So let me remind you the formula. Let me just squeeze it up here. Formal charge is equal to group number minus half the number of bonding electrons minus the number of non-bonding electrons. That's the formula that we're using, right? So in the case of, let's say, carbon, let's do carbon first. What would be the group number of carbon?
4.
4. Minus half the number of bonding electrons. So how many bonding electrons does carbon have?
6.
6.
3.
Right? Minus the number of non-bonding electrons, which for carbon in this case will be 0, right? So that's 4 minus half of 6, 4 minus 3. So the formal charge on the carbon here will be +1. All right? We're going to do a similar calculation for the chlorine. What's the group number for the chlorine?
7.
7 minus half the number of bonding electron, which is what?
8.
Huh? Bonding electrons.
Oh.
Remember, by the way, let me remind you, the same calculation for this would apply to this as well. So we're just doing one calculation and apply it to both of them, right? So for this chlorine atom, how many bonding electrons does it have? 2. And then minus the number of non-bonding electrons. How many non-bonding electrons do we see here? Hmm?
6.
6 would be the answer, if that's what you said. Okay, so 7 minus half of 2, so that's 7 minus 1, that's 6 minus 6, 0. So therefore, there's no charge on the chlorine. Then we do the same calculation for the oxygen. What's the group number for the oxygen?
6.
6 minus half the number of bonding electrons for the oxygen, which is what?
2.
2 minus the number of non-bonding electrons, which will be what?
6.
6. So this gives you -1. So the oxygen here has a -1 charge. All right. So here we have a situation where one atom has a negative charge bonded to directly an atom with a plus charge. So what will happen in this case is that this pair of electrons will come down here to form a second bond, right? In so doing, the negative charge here will cancel out the plus charge here, right? So the final answer, we'll just create some space here. Final answer, let me erase this here. Okay, so the final answer, when the electrons move from here to here, the final answer is going to be Cl, C double bond O, and then Cl, and that would be it. So this here would be the final answer for the Lewis structure of COCl2. All right? Any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Oh, by the way, let me make sure I get everybody's attendance. In the meantime. Okay, let's see here. Akil. Not here. Brown?
Yeah.
Okay. Browning. Let's see Browning. Davis is here. DeGraw is here. La Fortune
Here.
Lush. Let's see Lush. My friend, oh, I got my friend O'Brien. is here. Rodriguez. Scalf. Or Scalf is here. And Worthlin. Oh, Lucius here. What did I just do? All right. So. Rosa. Okay, so there are no questions about this one. Let me clear all of this here. I want to keep the formula for calculating point charge. So this is the formula, half the number of bonding electrons minus the number of non-bonding electrons. Okay, so the next question is asking for you to do the same thing for sulfur dioxide. So SO2. So tell me the steps to take. First step is what?
Total valence.
Okay, so sulfur will contribute how many?
Sulfur would be 6,
And oxygen will contribute how many?
12.
12, 6 times 2. All right? So that's 18 electrons, which will equal to 9 pairs. All right? What's the next step?
One with least electronegativity.
Okay, which one would be in the middle?
S.
Yes, will be in the middle, and then we surround it with oxygens. And then what?
Bonding.
Okay, so 1, 2, then what?
Surrounding pairs are not.
Okay, 3, 4, 5, 6, 7, 8. And then the 9th pair would go where?
Go with the.
On the sulfur. Okay, very good. So the next step is
Formal charge.
formal charge. So for the sulfur, how do we calculate the formal charge? Remember, this is the formula right here, right? So how do we calculate the formal charge for the sulfur based on that formula?
Number 6.
6 minus,
Minus half the bonding electron.
which is how many?
Should be 4.
Okay, minus,
The non-bonding.
which is
That 2.
2. So that's 6 minus 2 minus 2. That gives you plus 2, right? Okay, and then we do the same thing for the oxygen. So first step in this case,
That's 6 as well.
6 minus
Half the bonding,
half of the number of money, which is what?
which is 2.
2 minus
And 6.
minus 6, which will be the number of non-bonding. So that'll give you minus 1. So the sulfur will have a plus 2 charge, and each oxygen will have a minus 1 charge. So based on what we did in the previous example, what do you think is going to happen in this case? We have 2 negative atoms. I'm sorry?
It's gonna be double bonds.
Exactly, you're gonna have 2 double bonds being formed. Because what's gonna happen is that this pair of electrons will come down here. This negative charge will cancel out one of these 2 plus charges. This pair of electrons will come here. That negative charge will cancel out the remaining plus charge. So therefore, the final answer is gonna be double bond S, double bond O. And that's it. All right, so that would be the Lewis structure for sulfur dioxide. Okay, any questions about this one? Any questions? Okay, let me clear this. Okay, what's the next? Okay, silicon dioxide. Let's look at that one. So. SiO2. Okay, what's the first step?
Valence electrons,
So silicon will give you how many?
4.
Right? And oxygen will give you how many?
12.
12. 6 times 2. So that gives you a total of 16 electrons, which will equal to 8 pairs. And then what next?
then you put least electronegativity in the middle, so starting by oxygen,
Mhm,
then the bonding pairs,
mhm.
the non-bonding.
So that gives you a total of 8 pairs, 2 bonding and 3 non-bonding on the oxygens. Okay, what next?
Formal charge.
Formal charge. So what's the formal charge? How do we calculate formal charge for silicon?
That's gonna be 4
Or,
minus half the number of bonding electrons,
which is?
which is 4
Mhm.
minus non-bonding, which is 0.
Okay, so that gives you a total of 4 minus 2, so that's +2. So the silicon is going to have +2. And then we do the similar calculation for oxygen, which is what?
6 minus half. Right. 2,
Half of 2 minus,
6.
right, so that gives you -1. So each oxygen will have a -1 charge. So what's gonna happen in this case is what you're seeing here. So you're gonna end up with. Oops. And that's it. All right, and that's how you get the Lewis structure for silicon dioxide. All right. 10:30, okay. I want to get to some other examples of Lewis structures when it comes to we call it polyatomic ions. So let me here it is. And go back to the PowerPoint to those examples. Okay, here we have 2 examples, right? Let's deal with the nitrate first. NO3 minus. Now, when it comes to ions, when it comes to ions, there's one slight additional step you have to take, right? And I'm going to demonstrate it using the nitrate ion, right? So we do like we did before. We count up the valence electrons. Nitrogen will contribute 5. Oxygen will contribute 6 times 3, gives you 18. But we also have to take into account the presence of a negative charge. And the way we do that is that for each negative charge that is present in the ion, you add an electron. For each negative charge that is that the ion has, you add an electron. And conversely, because we're going to see maybe 1 or 2 examples of positive charges, for each plus charges, you remove an electron. All right. So for each negative charge, you add an electron. For each positive charge, you remove an electron. So in this case here, in addition to the 5 and the 18 electrons that we have here, because of the negative charge, we need to add 1 more electron. Right? So the total number of electrons involved here in this case would be 24 electrons, which would be equal to 12 pairs, right? And then we do like we did before, we put the nitrogen in this case in the middle, surrounded with the oxygens, and then we put the bonding pairs 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have assigned all 12 electrons, or all 12 pairs of electrons, right? The next step, like we did before, we calculate the formal charges. Let's start off with the nitrogen. What's the formal charge on the nitrogen? Well, according to the formula, the group number would be 5 minus half the number of bonding electrons, which for the nitrogen would be 246, minus the number of non-bonding electrons, which would be 0. So 5 minus half of 6, which is 3, that will give you +2, all right? Then we do a similar calculation for oxygen. The group number is 6 minus half of 2 minus 6, and that gives you -1, right? So the nitrogen here will have a +2 charge, and each oxygen will have a -1 charge, right? So we do something similar to what we did in a situation like this, where we can move 1 pair of electrons here to form a double bond here. So this negative charge will cancel 1 of the 2 plus charges. Now here's where you might be tempted to do another step, which would be incorrect. And that is, you might be tempted to move another pair of electrons from here to here, but that is not correct, right? And the reason why is because nitrogen is in period 2, right? when it comes to elements in periods 1 and 2, those elements cannot have more than 8 electrons on their outer shell. All right, so if you were to move this pair of electrons here and move this pair of electrons here, this nitrogen will end up with 1, 2, 3, 4, 5, or 10 electrons on its outer shell, which is impossible. So we can only move one pair of electrons from here to here, right? So I'm going to write down this resulting structure from that. So the resulting structure will be this. Minus, minus, and a plus charge here. All right, and that will be the final structure of the nitrate ion. All right, so please remember that elements in periods 1 and 2 basically, they cannot have more than 8 electrons on its outer shell. Now that is possible, having more than 8 electrons on your outer shell is possible for elements in period 3 and below. All right, and there's a term that is used, which I covered in the video. We say that those elements can expand beyond their octet. In other words, they can have more than 8 electrons on their outer shell when needed. All right, so that's what happens in those cases. But in this particular case here, the nitrate or the nitrogen cannot have more than 8 electrons on its outer shell. Okay, any questions about this? Any questions? Any questions? So let me see here.
You said 3 or below? Yeah.
3 and below can have more than 8 electrons on their outer shell, but elements in periods 2 and 1 cannot. All right. Okay. Okay, so let me go back to the PowerPoint. Okay, carbonate ion is the next one. So CO3, 2 minus. All right, so let's go through the steps. Carbon will contribute how many?
4.
4. Oxygen will contribute how many?
18.
Hmm?
Are there 3 oxygen?
Yeah, 3 of them, so 3 times what?
That's 6.
So that gives you 18, right? And then we have to take into account the -2 charge. So because of the negative charge, we have to add 2 more electrons, right? So this gives you a total of 24 electrons, which will equal to 12 pairs. And we put the carbon in the middle, surrounded with the 3 oxygens, right? So the first 3 pairs will go here, here, and here, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Then we calculate the formal charges. So the formal charge of the carbon will be equal to what?
Four
4 minus
minus
half of what?
6.
Half of 6
Minus 0.
minus 0, so that gives you +1, right? Okay, and then we do the same thing for the oxygen. So that will be what? 6 minus
Half of
2 minus,
6.
so that gives you -1. So in this particular case, each oxygen will have a -1 charge, and the carbon will have a +1 charge. So what do you think is going to happen in this case?
One oxygen will double bond.
Okay, so one of the oxygens will donate a pair of electrons to form an extra bond, like in that case here. So the final answer is going to be minus C double bond O, single bond O, and that's it. So this here would be the final answer. All right. Okay, any questions about this one? Any questions? Okay, I want to do one where the central atom will have more than 8 electrons on its outer shell. Let me see if I can find the example of that. Okay, one of these. Which one shall I choose? Eeny, meeny, miny, moe. All right, let me choose SO4 2 minus. So I think this is gonna be the last one for today. Okay, so SO4 2 minus. Okay, so first step will be what?
And electrons,
So sulfur will contribute how many?
6,
And then oxygen will contribute how many?
6,
6 times
4,
4, 24 electrons. And because of the -2 charge,
yeah,
we have to add 2 more, right? So that gives you a total of 32 electrons, which will equal to 16 pairs, right? So we put the sulfur in the middle and we surround it with the 4 oxygens. All right? So we put the bonding pairs first, 1, 2, 3, 4. Then the non-bonding pairs, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. All right? So, next step.
A formal charge.
Okay, formal charges. So let's calculate the formal charge for the sulfur first. How would we calculate that?
6 minus half of 8 minus 0,
So that gives you what?
2.
Plus 2, so plus 2 here for the sulfur. And then in the case of the oxygen, how would you calculate the formal charge for each oxygen?
6 minus half 2 minus 7 equal.
-1.
Yeah.
So each oxygen will have -1 charge. All right, so what next? So what's gonna happen next?
One of the oxygens will give up one of, make a double bond to the sulfur.
Well, guess what? You can also have this happening. Another oxygen will donate a pair of electrons. Why? Because sulfur is in period 3. So therefore, sulfur can have more than 8 electrons on its outer shell. You see what I'm saying? So therefore, the final answer in this case, if I can squeeze it in this corner right here, would be S double bond O, single bond O, single bond O, double bond O. And that would be the final answer, right? So sulfur here, in fact, in this structure here, sulfur has 1, 2, 3, 4, 5, 6 pairs of electrons, right? Which is possible because sulfur is in group, I'm sorry, not group, in period 3, all right? Okay, so I think that would have to be it for today. So what we're gonna do is continue our discussion of assignment number 9 next week, all right? Because there's some other questions that we have to look at. All right, so that's pretty much it for today, folks. I'll see you guys next week. And for you guys out there in Zoom, I'm signing